This is a C2 Edexcel chemistry video on topic 5, chemical reactions, which is to do with exothermic and endothermic reactions, and also rates of reaction. So exothermic reactions, or exothermic change, is one where heat energy is given out. Okay, so examples of these are combustions and explosions. So exothermic reactions, endothermic is where it's taken in. So examples of this are like photosynthesis or ammonium nitrate in water. The breaking of bonds is endothermic, so to break bonds you need to take energy in, and when you make bonds, that's exothermic. Making new bonds releases energy. The overall heat energy change for a reaction is exothermic, is more heat, and if more heat energy is released making bonds than breaking bonds. So if more is released when making than breaking, that's exothermic. If more is required in breaking than making, it's endothermic. So make sure you get those two the right way around. Oops. Skip back to the right part of the video. So that's the basics of exothermic and endothermic reactions. They do show up in graphs quite often. So you need to look at the reactants and the products. Okay, so we have here the reactants and the products. On this axis you have the energy. You can see that there is this is an endothermic reaction, and this is an exothermic reaction, because the energy of the products is less than the energy of the reactants. Okay, in this endothermic reaction on the left, the energy of the products is more than the energy of the reactants. Okay, the initial rise shows the energy required to break old bonds. That's what that rise shows. Right, so the rise is the breaking and the fall is the making. So you can measure the temperature change that take place in any of the following four reactions, so like salts dissolving water, neutralization reactions, displacement reactions, and precipitation reactions. So any of those, you could measure the temperature change and figure out whether it's an exothermic or endothermic reaction. You can measure the amount of energy produced by a chemical reaction in a solution by taking the temperature of the reactants. So if you know the temperature of the reactants beforehand, this can sort of be done by mixing in a polystyrene cup. The reason why you'll do that is because it's an insulating cup, and then measuring the temperature of the solution at the start and at the end. If you figure out whether the temperature's gone up or down, you will know whether it's exo or endothermic. Remember, there will be some lost heat to the surroundings, so you try to keep it insulated. That's what's a polystyrene cup, but you also put a lid on the top as well. Right, so let's go to rates of reactions now. Now remember, anything to do with the word rate is to do with how quickly something happens over time. So different reactions can happen at different rates. So they can happen very, very quickly, so in a short period of time, or very, very slowly over a long period of time. So weathering of rocks is a slow reaction, has a low rate of reaction. Explosions are fast reactions, have a high rate of reaction. So there's two ways to measure the rates of reaction. You measure the rate at which a reaction is used up, or the rate at which a product is formed. So when products are what come out of reactions, reactants are what go in. So you need to measure the rate at which one of these is being used up, so how quickly it's being used up over time. The method chosen depends upon your reaction being studied. So if you're trying to, if your if your product is a gas, it's quite easy to measure how much gas is given off, or you could measure the mass loss by that gas escaping, and how quickly that mass loss occurs. And the measurement itself depends on the nature of the reactant or product. Okay, so if it's the mass of a substance, a solid, liquid, or gas, it's measured with balance. If it's a volume, it's usually done with a gas syringe, or sometimes an upside down measuring cylinder or burette, sometimes put underwater. So to measure the rate of reaction, you need to do the amount of reactant used, or the amount of product formed, divided by time. Okay, so remember, rate is always this idea of something divided by time. So 24 centimeters cubed of hydrogen gas. Let's just make that really obvious. 24 centimeters cubed of hydrogen gas is produced in 2 minutes, and the rate is 12 centimeters cubed of hydrogen per minute. So how can we actually increase the rate of reaction? Well, there's a few processes that we need to get our head around. The rate of reaction can be increased if the temperature is increased, the concentration of the dissolved reactant is increased, the pressure of a reacting gas is increased. So look at the difference between those two. concentration if it's dissolved reactant, and pressure if it's a reacting gas. Or if it's solid, if it can be broken in smaller pieces, therefore increasing the surface area, or by using a catalyst. So what actually happens is the rate of reaction is faster, but it still forms a total amount, the same total amount of product. Okay, so this one's happening slower, but it still levels off at the same point. It still stops reacting at the same point. So the graph summarizes the difference in rates of reaction with different temperatures, concentration, and size pieces. The steeper the line, the greater the rate of reaction. So the blue line is the greater rate of reaction. Reactions are usually fastest at the beginning when the concentration of reactants is greatest. When the line becomes horizontal, the reaction is stopped. Remember, the line stops increasing, I should say increasing, at the same point. The faster reaction gets, the faster reaction just gets there sooner. So it's just happening at a faster rate, it's just getting there sooner. All of this is sort of summarized, the understanding of why the factors affect the rate of reaction is explained by this idea of collision theory. You've got to be able to explain what actually happens in these reactions in terms of particles and their collisions, and saying why these changes in conditions lead to a faster rate of reaction. So when chemical reactions take place, particles must collide. The collisions with too little energy do not produce a reaction. So collisions must occur of sufficient energy. So the collision must have enough energy. The minimum energy needed for a particle to react is called the activation energy. So it has to have at least the activation energy for a reaction to happen. So change in concentration or pressure, what does that actually do? What you're actually doing there is you mean there's going to be more reactant particles in the same volume, therefore there's a greater chance of particles colliding, therefore the rate of reaction increases. So there'll be more reactant particles in the same volume that have the activation energy, therefore there's a greater chance of the particles colliding and transferring that activation energy, therefore the rate of reaction increases. The solid is now broken into smaller pieces, the surface area is increased, more particles are exposed to the other reactant, there's a greater chance of the particles colliding with the activation energy, therefore the rate of reaction increases. Temperature. So the temperature is increased, the reactant particles move more quickly, more particles have now got the activation energy or greater than it because of the fact they've been given more energy. The particles collide more often with the activation energy, and more collisions result in a reaction because of the fact that more have the activation energy. Therefore the rate of reaction increases. What a catalyst does is it speeds up the rate of reaction without being used up. It does this by lowering the activation energy. Therefore, more collisions, more particles will actually have this new activation energy, and therefore more collisions will be successful, and therefore it increases the rate of reaction. Different reactions need different catalysts, and catalysts are important in industry because they reduce costs. So remember, catalysts reduce the activation energy, meaning more particles can actually create a reaction. Catalytic converters in cars have a high surface area to increase the rate of reaction of carbon monoxide and unburnt fuel from exhaust gases with oxygen from the air to produce carbon dioxide and water. So there's these unburnt fuels that have hydrogen within them. There's carbon monoxide, which is a dangerous fume. Catalytic converters have this large surface area to make sure that carbon monoxide becomes carbon dioxide and the unburnt fuel ends up essentially becoming water. These catalytic converters also work best at high temperatures, so that's why they're very useful in the engine of a car.